Okay, here's our second example. In the first example, we only had minimum stirrups throughout. So in this example, hopefully we will get to where we need more than minimum stirrups, and I call those strength stirrups. The problem is as before, there's a center-to-center spacing of 20 feet, a support width of 1 foot, but the loads are much higher. Okay, so with these much higher loads, hopefully we'll get into region 3 and maybe even region 4 on our shear design chart. We'll do the flexure design as before. You estimate the self-weight, you get the moment. Again, we're trying to shoot for this 1% steel, which means, remember in that lecture, I said that VC will be 2 square root F prime C BD if rho is less than 1 point, I think it was like 1.6%. I can't remember the exact number. But this is below that, so we will be using the 2 root F prime C equation for VC. Now, once you get the Rn, you get the required BD squared. It's much bigger beam this time, 16 inches wide and 30. So the beam is now 16 by 30, and D is now 27.5 inches. Then we update the actual self-weight, get the new moment, get the new rho just a little below 1%, choose a steel, have to round up quite a bit, but I'm pretty sure the rho is still less than that 1.68%. Either way, we're going to use that 2 root F prime C in this class. Okay, here's the approximate shear envelope again, where this is WU L over 2, and this is 1.6 W live L over 8. Okay. And this time I got smarter. I divided by phi first before I did all the chopping stuff. So here's divided by 0.75. Okay, and then here are the calculations. There's the slope, 131.7 minus 21.3 divided by 10 feet. D from the face of the support is D plus width over 2. It's the same 2.79 feet. Oh no, D is bigger now. So 2.79 feet, a little bigger. Delta V is M times delta X, 30.8. And you subtract off and you get 100.9. Okay, I've been thinking about this quite a bit. Typically, the height of your B is about 1/10 to 1/12. Okay, and so that means that this is about, because it's about D, not quite exactly, but that's L over 10 to L over 12. And this is L over 2. And so we're coming out 1/10 of 1/2. And so it's 1/5. And so what I'm guessing is roughly, if you take 80% of your maximum shear, you could get close to that cutoff value. Let's see if that works. 131.7 times 0.8 is 105.3. Close to that. It's not quite, because I assume this thing went down to 0, but it actually goes to a mid-span value. Okay, anyway, you can forget all of that. It's just, I like to come up with ways to double check things. So I feel comfortable that this is correct, but I knew it was right. I mean, we did all that, but it's always good to double check things. So here's our design chart again. These numbers change slightly because the D is bigger and the B is bigger. And so here we go. This example, I've written out more of the steps. Okay, so if you put 2 square root 4,000, it was 16, and D was 27.5. 27.5. Okay, times 27.5. It's all scary when I double check my PowerPoint slides, but let's do that. 4,000 square root 16, 27.5, 55,660, or 55.66 kips. Okay, half of that is 27.85. This is 50 times BD. Remember, this is always in pounds. 77.66 kips. 3DC is 166.9. So the numbers we're looking for, okay, and we'll see if we have them, are 27.83, 77.66, and 166.98. Let's look. Yes, so we go all the way up to 100.9. And so we are very, very likely, even after we shift the boundaries, we're very likely to get into here, and we are not above 167, so there's no region 4. Okay, so here they are. Those are the numbers. Okay, and remember, our biggest shear was 100.9. Okay, so we don't need this because we only go up to 100.9. Okay, here they are. We've done this before. I should be able to skip the details, but well, let's just do it. How did I get this 0.59 feet? Okay, the slope was, let me go look it up, 11.04 kips per foot. Okay, so let's call this delta x1, delta x2. So rise over run, 27.8 minus 21.3 over delta x1 will equal 11.04. Delta x1 equals, let's see, 27.8, 21.3, divide by 11.04, 0.59 feet. And similarly, we'll do it, 77.7 minus 27.8 all over delta x2 equals the slope, delta x2. I'll bet you dollars to donuts comes out to 4.52. Okay, 77.7, 27.8, subtract that, divide by 11.04, 4.52 feet. Okay, so we should have a pretty significant region 3. Let's continue. Okay, region 1, no stirrups. Again, I do not recommend doing that. Okay, region 2, let me go get the equation. We're going to use this, okay, and less than that. Okay, so region 2, there's that equation. Again, we're using the number 3, 60,000, 50, 16, 16.5, but cannot be more than 13.75. And so I'm rounding down to 12. So we went from 16.5 to 12. That's not as drastic a change as that previous example, but it'll be different. So before we do it, the boundary was 77.7, and if we're lucky, the new boundary is more than 100.9, and we don't have a region 3. But I know there's a region 3 because I made this problem. Anyway, 60 AVD, the real S, not the calculated one, not 16.5, 12, 30.3 kips, and we get 86, less than 100.9, we do have a region 3. Okay, so region 3 now, Okay, so here we are in region 3. We're going to use this equation here. So this is something new. We didn't have this in the previous example, but it still has to be less than d over 2. So here we go. You can get a different spacing for every VU, but we're going to just do it for the biggest shear and solve for that. So let me rewrite that there. VS is the VN required minus the concrete. That difference is how much you have to have in the stirrups. So the biggest shear on region 3 was 100.9, and the VC was 55.7 kips. So we're short 45.2 kips. The steel has to provide 45.2 kips of shear, and that's VS. So here's that equation. We're still using the number 3's, AV, FY, D, divided by VS. That's how much we need. Okay? We get 8.03 inches. S max, D over 2 is 13.75. We're going to use number 3 at 8 inches. Okay. Oh, and the new boundary, remember, was 86 kips. Okay, so I changed that to 86, and that made this number a little different. Okay, so very roughly, so if you take 4.14 feet and divide it by 8 inches, so 4.14 times 12 divided by 8, that's 6.2 spaces. And if you take 5.27 feet divided by 12 inches is 5.27 spaces. Okay, and what we need to do, you obviously can't have fractional spaces, so we have to make it all add up. So what I did was I did 6 spaces, and I know it's shorter than 6.2, but let me show you. That's this here. Oops, sorry. Let me try that again. That has to cover this 4.14 feet. There's this extra 6 inches here. You don't need a stirrup over the support. And you could even move this as much as, I feel you can move it as much as half a space. But let's figure out what this is in inches. So 4.14 feet is 49.7 inches. Let's say 50 inches. And 6 at 8 is 48 inches. But you already have this extra 6 inches there. So it has to be at least this. We've actually gone more than that. We've gone 48 plus 6 equals 54 inches. So that's fine. We've gone farther than the 50. This is good. Okay, that's how I figured that out. Okay, and then what I did then was I did not have, I took out this region 1. I put minimum stirrups everywhere. So then what I did was I figured out, okay, that's 54 inches. If I did that right. Oh, what's that? That's 4 feet 6 inches, right? Okay, that means that is 4.5 feet, which makes this 11 feet. Okay, and that divides into 12 inches exactly. So that's the final answer. Okay, and so there are a total of 6, 12, 23 spaces, means 24 stirrups. Okay, now sometimes it doesn't divide nicely like this, and so you might get a situation where you have a beam like this, and you've got a certain kind of spacing here, a certain kind of spacing here, and then these don't quite divide correctly. What you can do, you can just say something like 13 stirrups spaced to fit. If you have to do something like that, spaced to fit. This little detail of making this all add up is harder than it looks. It worked out perfectly for this example, but this can be harder. Okay, so that is example number 2.